Okay. Now, in the previous lecture, we've introduced the notion of a matrix being in echelon form. So let's recall what that means here, as in this definition. A matrix, n by n matrix, is in echelon form if, first of all rows that consist entirely of zeros are grouped together at the bottom of the matrix. So the 0 rows are down in the bottom. Secondly, in every non-zero row, the first, when you count from the left, the first non-zero entry is a 1. Okay. Thirdly, if the I plus first row contains non-zero entries, then the first non-zero entry of the I plus first row is in a column to the right of the first non-zero entry of the ith row. So the example being here, right, the first non-zero entry, which is supposed to be a 1 in the ith row, is here. The first non-zero entry of I plus first row is here. That's to the right. And in addition, a matrix in echelon form is in reduced echelon form. Reduced echelon form if the first non-zero entry in any row is the only non-zero entry in its column. So the condition here being imposed is this only condition, that every entry, the non-zero entry here, this 1 here, this sits in this column is the only non-zero such thing. Okay, and we've seen examples. And now let's see one more example of echelon forms. Say matrix called D. This is 1 minus 3, 1 0 0 minus 3 0 0 and 0 1 0 4 minus 5 0 2 1 0. Let's suppose this is an augmented matrix. So the corresponding linear system is x1 minus 3x2 plus x4, not x4, 4x4 equals to 2, and x3 minus 5x4 equals to 1. And then you have a 0 row. The third row here, as you can see, is a 0 row. So that doesn't give you any useful equation. Now, how are we supposed to solve for this? Right? You can do the following. Going back a little bit to the augmented matrix, here you have the first non-zero entry, here you have the first non-zero entry. They correspond to this x1 and this x3. So what we're going to do is expressed using these equations. These corresponding variables in terms of everything else. Okay. So certainly these two are just equivalent to the two equations we have. And also you observe that x2, x4 can be arbitrary. Okay. And this describes all solutions. Once you pick the values for x2 and x4, these equations give you the values for x1 and x3. Okay. So let's do one more example, maybe. Examples. 1, 0, 0, 0, 1, 0, minus 1, 3, 0, 0, 0, 1. Now the corresponding, this again, let's assume, let's just consider this as, I don't want that. Let's just consider this as the augmented matrix for some linear system, and then the linear system is okay. The first row gives us x1 minus x3 equals to 0. The second row gives me x2 plus 3x3 equals to 0. The third row gives me 0 equals to 1. And you see here's a problem. Zero is not equal to 1. 0 cannot equal to 1. This is impossible. And what this means, because such an impossible equation occurs in the system, this means that the system has no solution. Or as we call such a system, inconsistent. Okay, and the reason for being inconsistent here is that you have this equation 0 equaling 1. And that equation comes from the bottom row, this row, where everything is 0 except for the last. So such a row, first of all, it's a non-zero row, and the first non-zero entry is a 1. And there's only one non-zero entry that happens on the last. So in fact, this is a more general phenomenon. So let's state the fact. And so suppose let's use this symbol here. A, B is the augmented matrix for a linear system. And this symbol is meant to meant to describe, say, A here as the coefficient matrix, and B here is the constant. Okay. Now, suppose this is the case. Suppose this is the augmented matrix. Then, if and oh no, not yet. And suppose AB is in reduced echelon form, if AB has a row of the form O0 with just a single one in the end, then the system has no solution. And the converse also holds. Okay, so this fact here is a way to recognize when the system has no solutions. If you happen to do all the work and run the process to get the augmented matrix into a reduced echelon form, and you see a row taking this form, then you see that it doesn't have the system does not have a solution. And the reason is simple. It's because such a row give you equation 0 equals to 1, and that equation is never good. Okay, so now okay, now what do we do? Now let's discuss how to reduce a matrix into a reduced row echelon form. Oh, all right. Reduction to reduced echelon form. So we can formalize the reduction process into an algorithm. Let's give it here. So step 1. Locate the first, or should I say leftmost column that contains a non-zero entry. Okay, do that. Step 2, if necessary, interchange the first row with another row so that the first non-zero column has a non-zero entry in the first row. Okay, so now next step, if A is, say this number A is the leading non-zero entry, in row 1, multiply each entry in row 1 by 1 over A. Or rather, multiply row 1. Okay, so we see that the second step, this second step uses possibly an elementary row operation, right? And the third step also uses such a one row operation. You can multiply a row by a non-zero constant. Now next step, step 4, add suitable multiples of row 1. So you take row 1 and you want to use it to get rid of non-zero entries in the lower rows. So add suitable multiples of row 1 to each of the remaining row so that every entry below the leading one in row 1 is 0. All right. Again, this uses one of the elementary operations that row operations that we've talked about. You can take one row, multiply it by a number, and add the resulting thing to another row. The next step, step 5, temporarily ignore the first row of this matrix and repeat steps 1 through 4 for the submatrix that remains. Okay, so basically that's what what exactly this is saying. Just forget about the first row for now and focus on the remaining part of the matrix and run the steps again. Find the first non-zero entry and move it to top row and make it 1 and get rid of everything else below it. And you may have to do this over and over, but there's a point where you need to stop. That is to stop when the resulting matrix is in echelon form. Okay. Okay, now after you're done with step 5, you should arrive at a matrix in echelon form. Now, the next step just takes it to reduced echelon form. Proceeding upwards at multiples of each non-zero row to the rows above in order to turn all entries above the leading one into 0. Okay. Over in step 4, from the perspective of leading ones, over here in step 4, you've already turned, for any given leading one, you've already turned entries below it to 0. Now the last step is to turn the entries above each leading one to 0, and that's what this step is supposed to do, and that in order to satisfy the requirement of being in reduced echelon form. Okay, let's do this in an example so that we this being stated as an algorithm is making things look formal. Let's do this in example because we should keep in mind or sort of find out, keep in mind as to what we really want to do rather than memorizing the steps of the algorithm. Okay, now, so here's a rather large example. Okay, so it's a rather large example. This is 4 by 7. All right, so let's try to turn this into reduced row echelon form. Okay. Now, let's first of all, what is the first step? The first step wants us to find the leftmost column that contains a non-zero entry, and that would be this column. And then you want to move one of the rows containing that first non-zero entry to the top. So for that matter, we do we exchange R1, R3, and we follow that by multiplying the new R1 by 1/3. Okay, and the outcome is this. Let me just write down the answer. Mm-hmm. 8, 11, 8, 17, minus 4, 11, 9, 4, 21. Okay, so what happened is we switched R1 and R3, the row 1 and row 3, and then we rescale the new row 1 by 1/3. Now, okay, so now this entry is, hold on. Now this entry here, this entry here is 1 now. It's the first non-zero entry. It appears in row 1, so very good. Now what the next step tells us is to make all the entries below this leading one 0. That's what step 4 tells us to do. And in this example, this leading one sits in row 1, so the only entries below it, and 2 of them are already 0. And there's just one non-zero such entry, that's a -2, so we know what we need to do next. We need to take R4 and add 2 copies of R1 to it. And that will give us the following matrix. Zero minus 1, minus 3, 3, 2, 0, minus 8, 11, 8, 1, minus 11, 9, 4, 1. No, minus 1. All right. Okay, so now the first row looks good. The next step to be performed is step 5, which tells us to ignore the first row and repeat the first 4 steps for the submatrix that remains. First row in this case is here, so we should ignore it for now and look at the submatrix, which is just the one that's the part that's not shaded. So then what do? We find the first, for that we find the first non-zero, first column containing the non-zero entries, and that's this one. And we also need to make sure the first row contains contains a non-zero entry in this column. That's already worked out. That's right here. So the next thing to do is to eliminate or turn entries below this one here into 0. Now this guy is already 0, so it's just this -1 that we need to take care of. Okay, so let's see here. So we do R2 plus R4. Okay, do that. R2, sorry, R4 plus R2, because I want to change the R4. So now the new matrix is 0, 0, 0, 1, 3, 11, 9, 0, 0, 0, 0, 2, 8, 4, 0, 0, 0, 0, well, 1 minus 1, that's 0. 3, 0, that's 3. 11, 1, that's 12. 9 minus 1 is 8. Okay, so now what? Now this is, now what are we supposed to do? We've taken care of the first entry, sorry, the first row. We've also taken care of the second row. Now we ignore them and run the steps for the remaining matrix, which is just these two rows. And again, what to do? What we need to do is to identify the column, the first column, the leftmost column containing a non-zero row, a non-zero entry, and that's this. And the first row already has one non-zero entry in this column, so that's good. Now what we need to do is to get rid of the other one. Yes. But for reasons that will become clear later, here's one. No, I guess it will be okay either way. So we will therefore do the following: R4 minus 2, 3, 2/3, not 2/3, 3/2 of R3. Okay, now the resulting matrix is okay. Sorry, there's one thing I should have done before. I should first turn this 2 into a 1. So that requires I half the R3, and I take R4 minus 3 times this resulting R3. Okay, that's better. I have the R3, that'll give me 1, 4, 2. And I take R4 and subtract 3 copies of R3. 3 copy will make this 3, and that's canceling this 3. So 0 here. 3, 4, that's 12, canceling with this 12. 3, 2, that's 6. A minus 6, that's a 2. Okay. So now what have we done? We've done all the steps for we've done all the steps for these matrices, but the submatrix containing the last 2 rows. And now what we need to do is to ignore the first 3 rows and run the steps for the last row. There's just one thing to do: turning this one single non-zero entry here into a 1. Minus 4, 0, 0, 0, minus 1, 1, 0, 0, minus 3, 3, 1, 0, minus 8, 11, 4, 0, minus 11, 9, 2, 1. Okay, so now what am I supposed to do next? Right, so now as you can see, this is a matrix in echelon form. The leading ones are here, 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 and here. And in order to be in reduced echelon form, we need the entries above these leading ones to be 0. And that is, that doesn't mean we need to erase them. The entries that we need to become 0 are here, here, and here. Okay, so here's what we're gonna do. We're gonna so we will do this. We will now run the last step. Just multiply one, add a multiple of one row to another. And more precisely, in this case, we need to do R1 plus R2. So that will keep R2, R3, and R4. Okay, and R1 becomes the following. Now this minus 1 is cancelled with this 1. Minus 3 adds, 3 added to minus 3, that's 0 now. 11 adds to minus 8, that's 3. 9 adds to minus 11, that's minus 2. Okay. So let's mark these, let's mark these entries again. The leading ones are still here. And the entries that still need to be turned 0 are these, here and here. Right. Okay, so now that's the next one to deal with is this one, 3 here. Now, so the operation to do is what do? We take R2, we minus 3 copies of R3. Okay, now this operation will keep R1, R4, and R3. So 0, 1, minus 4, 0, 0, 3, minus 2. R3 and R4 remain the same, so 0, 0, 0, 0, 1, 4, 2, 0, 0, 0, 0, 0, 0, 1. Now R2 is changed. It's still 0, 0, 0, 0, 1. Now this 3 here is subtracted by 3, so that becomes 0. Now over here, you have 11. The next entry, you have 11 minus 4 times 3, that's 12. So it becomes negative 1. Okay, the next entry, you have 9 minus 3 times 2. That's 6. 9 minus 6, that's 3. Okay. Now what do we have? The leading ones are still where they are. The entries that still needs to be turned into zeros are now these guys. Okay, Very good. So now we can proceed quickly. We're gonna take R1 and add 2 copies of R4. We're gonna take R2 minus 3 copies of R4. We're gonna take R3 minus 2 copies of R4. And doing that will effectively cancel these entries without changing anything else. So we will end up getting three minus 1, 4, 0, 0, 0, 0, 1. All right. Again, the leading ones are here. Now, leading one entries above or below leading ones are all 0 now. So this is in reduced row echelon form. Okay. All right, so very good. In general, this is how you turn a given matrix into its reduced row echelon form. The process can be tedious. It certainly usually is lengthy, but you get there. Right? It takes a while, but you get there. So now once again, now we have, we've described the steps for solving a linear system. Now we can sort of say that again in more precise terms. So what would we do? Solving a linear system. Step 1. Oops. Step 1 is to consider the augmented matrix corresponding augmented matrix. Step 2, transform the augmented matrix into reduced row echelon form. Okay, using the method that we described above. Next step, convert. Now that, after doing step 2, you get a matrix in reduced echelon form. That matrix should be viewed as the augmented matrix of some linear system. So convert the reduced matrix to a linear system. Okay. And the point of doing all this is that this new system should be simpler but equivalent to the original system. Being equivalent here just means that they have the same set of solutions. So for our purpose of solving the system, it's enough to work with the simpler system. Now the final step is just to read off solutions from this simpler system. Read off. Okay. Oh, well, let's see here. So this is the plan, and maybe we can do an example that's somewhat complicated. We will save some time by omitting some steps in the reduction process. So let's say you have in this example 2x1 minus 4x2 plus 3x3 minus 4x4 minus 11x5 equals 28 minus x1 plus 2x2 minus x3 plus 2x4 plus 5x5 equals minus 13 and minus 3x3 plus x4 plus 6x5 equals minus 10, 3x1 minus 6x2 plus 10x3 minus 8x4 minus 28x5 equals to 61. Okay, 4 equations, 5 variables. Okay, so that's a 4 by 5 system. So in order to solve it, the first thing to do is to write down the augmented matrix. Okay, and that's sort of the easiest thing that we need to do. You extract the coefficients and the constants and line them in the correct places. If a term does not appear in an equation, it just means that the corresponding coefficient is 0. Okay, so this is the augmented matrix. If you like, you can separate these two. Oops. Now we need to do, one of those things. Turn this into reduced row echelon form. It's not, if you just try to follow the steps, it's not super simple. So here we're gonna do something slightly different. The first, well, not that. We already know that the first column contains the first non-zero entry in any row. So if we do this, R1 plus R2, we would keep R2, R3, and R4. As this. And R1 plus R2 would be the following. 2 minus 1 is 1. Minus 4 plus 2, that's minus 2. 3 minus 1, that's 2. Minus 4 plus 2, that's minus 2. Minus 11 plus 5, that's minus 6. 25 minus 13, that's what? 15. Okay. Very good. Now, why am I doing this? Yes, the reason to do this is now you get the leading term in first row to be on the far left, and it's a 1. So that's what we would like. And then the next thing to do is to use this 1 to cancel the entries below it. That is this minus 1 in row 2 and this 3 in row 4. We will do that now. So if we do that, that will be R2 plus R1 and R4 minus 3R1. R1 stays the same, R3 stays the same. Minus 2, 2, minus 2, minus 6, 15. R3 stays the same. R2 changed, right? 1 minus 1, that's 0. 2 minus 2, 2, that's 0. 2 minus 1, that's a 1. Minus 2, 2, that's 0. Minus 6, 5, that's a minus 1. 15 minus 13, that's a 2. Now, for the R4, 3 minus 3 is 0. Minus 6 minus 3 copies of minus 2, that's minus 6 also, so that's 0. 3 copies of 2, that's 6. 10 minus 6, that's a 4. 3 copies of minus 2, that's minus 6. Minus 8 minus 6, minus 8 minus negative 6, so minus 8 plus 6, minus 2. 3 copies of minus 6, minus 18. So that's minus 10. 61 minus 45. That's 16. Yes. All right. So now the first row is done. The next thing to do is here. This is the first non-zero entry in the remaining submatrix. And it happens to be a 1 already. So what you need to do is to use it to get rid of the entries below it. And above it, maybe. But well, let's do it below first. Well, let's in fact do the ones above it too, because we're going to need that for in order to get to reduce echelon form anyway. So let's say R1 minus 2 R2, R3 plus 3 R2, R4 minus 4 R2. And what do you get? R2 remains the same, everybody else changes. Let's just be a little bit quicker and agree that the answer is 1 minus 2, 0 minus 2, minus 4, 11. Okay. And here 0, 0, 0. 0 is here, so whatever you do, you don't change it. So it's 3 minus 4. 0, 0, 0. Minus 2, minus 6, 8. Very good. Now what? Now we've done. Now where are the leading ones? Leading ones here, here, and now it's this one. The third row, first non-zero entry already is a 1. So what you need to do in order to get to reduce echelon form is to get rid of these guys. Here we can do that. And the operations for that would be, so take R1 add 2 R3, and take R4 add 2 R3. They'll keep R2 and R3. And R1 becomes 1 minus 2, 0, 0, 2, 3. And R4 becomes, guess what, completely 0. Okay. Now again, let's identify the leading ones. Here, there, there. Is it in reduced echelon form? Yes, it is. Okay, reduced echelon form. Okay, very well. Now, the next thing to do for the purpose of solving the linear system is to convert this system back into, convert this matrix back to a linear system. For this, we should remember that this is supposed to be the augmented matrix. So the last column is the column for constants. And over here, you see that the bottom row here, row 4, is a 0 row. So that'll just give you an equation 0 equals to 0, which you can ignore because that does not contain any information. Converting back to a linear system. So the resulting linear system here is x1 minus 2x2 plus 2x5 equals to 3, and x3 minus x5 equals to 2, and x4 minus plus 3x5 equals minus 4. And again, the idea for reading off solutions is to take the variables indicated by the leading ones, just move everything else to the right hand side. These variables are going to be dependent variables. How do I do this? These variables are going to be dependent variables. Because they're going to depend, their values depend on the values of others. Okay, so if we do that, we would get x1 equals to 2x2 minus 2x5 plus 3. x3 equals to x5 plus 2. x4 equals to minus 3x5 minus 4. And x2, x5 can be arbitrary. Okay, so this is the solution. These are all the solutions to this linear system given. Okay, very good. All right, so That's the end of this lecture.